Assalamu alaikum. Bismillahirrahmanirrahim. The topic of our today's lecture is the translational mechanical system. This is the topic of your chapter number 2 of your book known as Nice. Earlier in the chapter, we have discussed how can we model any system in frequency domain, and in the few last couple of lecture, we have studied how can we find the transfer function of any electrical system in frequency domain. We use different techniques to model any system, electrical system, by using nodal mesh or any other technique. You can find the transfer function of the any electrical system. Today we will start the translational mechanical system. Before starting the translational mechanical system, you should know the basic components of the translational mechanical system. Like in electrical, we have three basic components. One is the capacitor, other is the resistor, and the third one is the inductor. Same in mechanical system, we have three basic components. These three basic components are the spring, viscous damper, and the mass. Like an electrical, out of three components, we have two energy storing components. Like in capacitor, the energy can be stored in the form of charge, and inductor is also in energy storing elements. Similarly, in mechanical, translational mechanical system, energy can be stored in spring and in mass as well. So we start the mechanical system. First of all, we will see the basic components of the translational mechanical system. One is the spring, and as we have seen the relation of the basic components of the electrical system, we have written the voltage current and voltage charge relation in case of electrical system. In case of mechanical system, we will write the force velocity and force displacement relation. Actually, whenever we applied force on any component, the result will be in the form of displacement or velocity. Okay. Similarly, first of all, we will check the relation of the spring. For a spring, when we will apply the force on one end of the spring, the result will be in the form of displacement. What is the K? K is the impedance of the spring. The relation between them is the f of t is equal to k integration 0 to t v of tau deta. It's similar to the relation of the capacitor. When we write the relation of the capacitor, voltage relation of the capacitor, in case of capacitor, the relation is v of t is equal to 1 over c integration I dt. Similarly, the force displacement relation of the spring is f of t for applied force equal to k x of t. X of t is the displacement, right? And for the impedance of the spring is k. Okay, and the second components of the translational mechanical system is the viscous damper, and the viscous damper for the applied force f of t is equal to fv of t into v of t. What is the f of v? F of v is the coefficient of the viscous friction. And for the relation, force displacement relation of the viscous damper, f of t is equal to f of v dx t by dt. And what will be the impedance of the viscous damper? That will be the fv into s. And for the mass, we can write the relation in the same manner as we have written for the other two components. Actually, if we resemble or the three components of the mechanical system with the electrical system, we can see the relation of the mass resemble with the inductor. Like inductor, if we write the relation between the voltage current, we have v of t is equal to L di by dt. Similarly, here it's m dv by dt. As we have replaced, we have resembled or we have replaced current by the velocity. These are the analogies between electrical and mechanical system. In electrical, we use the term electrical voltage, and mechanical we use mechanical force. Actually, in electrical circuit we always apply the voltage, and in mechanical we apply the force. For electrical system, there is the electrical current or mesh current. In mechanical we have mechanical velocity. For electrical we have electrical charge, and for mechanical we have mechanical displacement. Similarly, as I have told you earlier, the components of the electrical are sorry, it's written wrong in the two columns. Actually, these will be in electrical column, capacitor, resistor and inductor, and for mechanical it will be the spring, damper and the mass. Okay, you can correct the last three rows of this table. Actually, it's mechanical component written in the electrical column, electrical written in the mechanical column. Similarly, for solution of the to find the transfer function of mechanical system, we will use the Newton's law. As in electrical system we use the Kirchhoff voltage and Kirchhoff current law. Similarly, we will write here the Newton's law. Actually, all forces that act on a body, either in the direction of motion or opposite to it, the mechanical system required just one differential equation of the motion. Actually, it depend upon the how many masses or how many what is the degree of freedom of the equation. Actually, in like in electrical system, we have checked that for the number of equations will be equal to the number of in energy storing elements. Similarly, here in mechanical system, the number of equations depend upon the degree of freedom. We will study further what is the degree of freedom. The degree of freedom, if our system have 1 degree of freedom, we have only one equation for that system. If our system have 2 degree of freedom or 3 degree of freedom, we have 2 and 3 equation of motion. Now for this system we have only 1 degree of freedom. Actually, in this figure we can see there are 4 forces. How there are 4 forces? One is the applied force, and the other 3 are the reaction force, or you can say one is due to the stiffness. Actually, when we applied force on the mass, then it opposes to the force. Inertia of the mass opposes the applied force. Similarly, the stiffness of the spring opposes the applied force, and the viscosity of the damper opposes the applied force. Right, basically there will be 3 opposing forces and one the applied force. Applied force is the F of t, and the other 3 forces, force consumed by spring, that is kx of t. K is the stiffness of the spring, x of t is the displacement. Frictional force, the opposing force is Fv. F of v, as I have told you earlier, this is the coefficient of viscous friction. And for the mass, that will be the this one. If we see the free body diagram of the given system, actually it's a system consists of one mass, one spring and one viscous damper. And when we applied force on the right hand side, you can see it's a free body diagram of the given system. Force is applied on the right hand side, and 3 opposing forces are acting on the left hand side. Okay, like in electrical system we have studied the voltage rise is equal to voltage drop. Similarly, here we will write the equation of motion. The applied force equal to the opposing forces, you can say. Applied force is the F, and the opposing forces are these. You have already seen these relation in this table. This is the force displacement column. For the applied force, there will be a displacement, and for the displacement we can write this relation. For mass, this is m d square x by dt square. plus f of v for damper dx by dt plus k of x. And if we write the relation between the output and the input, actually when we applied the force on the right hand direction, then there will be a displacement of in the right hand direction. You can see here it's x of t. Displacement will be in the direction of applied force. So F is equal to, if we convert this equation by taking the Laplace transform, as you have studied earlier, the equation will be in this form: F is equal to m xs square plus f bx of s plus kx. And if we find that if we write the transfer function, then a transfer function will be the output by input, and this will be the transfer function of the given system. Okay, now we have here we have two masses, m1 and m2, and the force is applied on the f on m1. Okay, as I have told you earlier that the number of equation in any mechanical system depend upon the degree of freedom of the system. How can we define a degree of freedom? Actually, in mechanical system, this system has 2 degree of freedom. How can you say it's 2 degree of it have 2 degree of freedom? Basically, in mechanical system, if this system has 2 degree of freedom, means one point of motion can be held still while the other point of motion moves under the influence of applied force. What does it mean? Means that if force is applied on m1, okay, then we consider that what will be the effect of force applied of m1 on the m2. Okay, and similarly that means when m1 is moving and m2 is still, or when m2 is still or m1 is moving. Basically, number of equations is equal to the number of linearly independent motion. Okay, so it has 2 degree of freedom. As I told, I will repeat it again, that linear independent implies that a point of motion in a system can still move if all the other points of the motion are still are held still. Means if m1 is moving and m2, let's suppose if we remove this viscous damper and spring between two masses, then these are connected with m1 is connected with the m2 without any other component between them. Then if we applied force on m1, then m2 is also m2 will also be in motion. In this case, we can held still one component while other component is moving. Okay, now we will write the equation. Actually, what we have to find transfer function x2 of t. X2 means the motion of the m2 by f. Actually, we are getting output at m2, and we have applied input at m1 for the given system. We will find all the forces on m1 and m2 separately. Now we will draw the free body diagram. Okay, you please keep attention on this slide. It's very important to understand the mechanical translational system. What this first block is showing. This first block is showing forces on m1 due to only the motion of m1. It means okay, when only m1 is moving. What are the forces applied on the m1? One is the f of t. F of t is the applied, and the opposing forces on m1. Actually, we are considering only the force on m1 due to only the motion of m1. We are assuming that only m1 is in motion while the m2 is still. Okay, then the opposing forces will be the stiffness of the spring k1 x1 as. Second force will be the due to the this inertia surface friction, due to this friction fv1, and we can write is fv1 as x1 of s. Now the third force is due to the inertia of the mass, that will be the m1 s square x1 s. We have already know the equations of mass, viscous damper, and the spring, right? And actually the components connected with the m1 are this spring k1, k2, fv3. This is basically this is the viscous damper, three components. Fourth is the frictional force, and fifth is the inertia of this mass. Basically one force is applied on m1 and five opposing forces are acting on this m1. Clear? I will repeat again. I have drawn a free body diagram method for 2 degree of freedom. Okay. As I told you earlier, 2 degree of freedom means we keep one body still and other body in motion. So for m1 we write force on m1 due to the only the motion of m1, and for this forces on m1 due to only the motion of m2. Means in this case only m1 is moving, m2 is still, and in this case the m1 is still and m2 is moving. Clear? If m2 is moving, what will be the effect of on m1? Basically two opposing forces are there, and the direction of these forces are away from the m1. You can see the direction of this when m2 is moving, and m1 is still, right? Then when m2 is moving, then this forces, this damper force and the spring, these both forces are acting opposite to the m1. Okay, if we combine all these forces, then we will get all forces on m1, right? We have combined the spring forces, frictional forces, inertia forces, and the applied force together. Okay, now we will see the next slide. Now in this slide we will consider that the forces on m2 basically there are two types of forces on the m2. One force due to its own motion, and second force due to the motion of m1 transmitted to the m2 through the system. As in the previous slide, uh, look here, we consider force of m1 due to only the motion of m1, and this is the force on m1 due to only the motion of m2. Means here the m1 is moving, m2 is still. Here the m2 is moving and m1 is still. Now this force due to the motion of m2 will also act on the m1. So in this slide we see for m2, when we find total force on m2, then we consider same. First we consider that m2 is moving and m1 is still. Then in the second diagram we will in this one we will consider that m2 is still and m1 is in motion. For this we consider that m2 is moving and m1 is still. Then there are five forces acting on the m2. There is no direct force or f of t applied on the m2. The five forces are opposing forces. One is due to this damper, this spring, due to this friction and inertia. Five opposing forces are acting on m2. We have written the equations in frequency domain of these opposing forces. One is the k2 x2 of t. Similarly for the friction, fv2 fv of 2, as its friction is the equation of friction is in first order. So as x2 of ts. Similarly, the equation of viscous damper is also a first order, and the equation of the inertia or mass is second order, and this is for x3 of this spring. Okay, now for this diagram which I have pointed out, we will consider that force on m2 when m2 is still and m1 in motion. When m will be moving and m2 is still, then only these two components are in motion, and the forces on m2 are k to x1 of s and this damper. Actually, when m1 is moving, the direction of force is towards the m2. You should consider the direction of forces. Actually, here all the forces are opposing forces, okay, and here it's also opposing forces, and the direction of the force is towards the m2, and here all forces on m2 that can be written in this. Okay, now we will sum the two forces. Basically, we will sum the forces of m1, and basically, as I have told you that we will write two equations of this system as it have 2 degree of freedom. Okay, uh, this is the forces on m1, and these are the forces of on m2. Then similarly, we will write this will be the equation of m1, in which the mass m1 on which the applied force we have applied the force, and this is the equation for the m2. As there is no applied force, so it will be the 0. Basically, these are the, so we have written simple, we have add these forces. We have taken x1 common, then m1 s square, fv1 fv3 plus fk1 k2 minus, we will minus these two terms as because of these forces the displacement is x2 not x1. Similarly, we have written the equation of m2. You can see how can we write the equation. Actually, first we have written the equation of x1 with the negative sign, as the direction of motion is x1 is opposite to the x2, and and these are the components related to the x2. Now we will find the transfer function. We have written these two equations, and the transfer function, what we have to find, we have to find the relation between the x2 over f of s. Now you can put this in the matrix form, and similarly by Cramer rule you can replace the second column with the fourth column, as we have done here. These are the equation we can put in the these are the coefficient of x1 and x2, then the displacement x1 and x2, and this is the column of applied force. It's similar to the if we recall the electrical system. Here we have voltage, here we have current, here we have voltage, here we have current, and here we have impedances. Okay, for to find x2, we will replace the second column with the fourth column, and by divided by the determinant, and we can find the relation between the output and input. Okay, now we will study how can we directly find the equation we can write the equation directly by the inspection. As you have studied in electrical system, sum of impedances connected with the, if you recall the loop method, the I1 and I2, if we have 3 loops, then we will write the sum of impedances connected to the I1 into I1 minus sum of impedances between loop 1 and loop 2 into I2 equal to sum of applied voltage. Similarly, here we will write sum of impedances connected to the motion at x1 into x1 minus sum of impedances between x1 and n2 into x2 equal to sum of applied force at x1. Similarly, when we write the equation of the second loop, we will write in electrical minus sum of impedances in the loop 1 common between the loop 1 and loop 2 into x1 plus sum of impedances in the loop 2 into I2 plus equal to the sum of applied forces. Similarly, we have written here sum of impedances between x1 and x2 into x1 plus sum of impedances connected to the motion of the x2 will be equal to the sum of applied forces S2. Actually, it's the method we have studied. It's a little complicated method, but it's conceptual. That how can we write the equation of motion in translational mechanical system? I will repeat again, that it depends upon the degree of freedom of the system. If the system have only 1 degree of freedom, we will write 1 degree of motion, only one equation of motion. If system has 2 degree of freedom, we will write the two equation of motion. So in this, and how can we write? We will first consider the mass 1, then we will consider the force on mass 1 when mass 1 is moving and m2 is still, plus we will consider the motion on forces on m1 when m1 is still and m2 is moving. Then we will sum these forces and we will get this force. Similarly, for m2, we will write this m2 when m2 is moving and m1 is still, and for this when m2 is still and m1 is moving. Right now, I think you should be more clear. And if we want to directly write the equation, then we will use this method. Clear? I have given you the example of electrical system, that sum of impedances in loop 1 into current I1 minus sum of impedances between the loop 1 and loop 2 into I2. Similarly, we can write this and try to write this equation directly by using this method. You will get the same result as we have got the results in free body diagram. Okay, now by using inspection method, we will find the transfer function of this again, as we have written sum of impedances connected to the motion of x1. Now check what forces are connected with the motion of x1. These are the m1, we have written this, then this frictional force, and which force? This damper force. We have written FV1, FV3 into S, as both are the first order, plus these two forces components K1 and spring 1 and spring 2, K1 and K2. We have written this minus sum of impedances between x1 and x2. And what are the forces that are between x1 this motion and x2 this motion? These are only two forces, FV3 and K2 into x2 is equal to sum of applied force. Applied force is F1. This is the same equation we have got from the free body diagram, and by inspection we can write the second equation for M2. Similarly, sum of impedances between x1 and x2. Now sum of impedances common between with the minus sign. Okay, this will be again these two forces and plus the sum of impedances connected to the motion of x2. These are 1, 2, 3, 4 and 5 forces, and we will write this 1, 2, 3, 4, 5 forces, and applied force is equal to 0. Okay, clear? Now I think the mechanical transmission system should be more clear to you guys, and now it's your task. Let's see how good your inspection skills are. Now you have to write the equations of this. First of all, you have to check how many equations you can write for this system. You can see this system has 3 degree of freedom. How 3 degree of freedom? We can move M1 by keeping M2 and M3 still. We can move M2 by keeping M3 and M1 still, and we can keep M3 moving by keeping M1 and M2 still. Okay. Now this system has 3 degree of freedom, and we can write the equation by inspection method. What will be the equation? Actually, this will be the sum of impedances connected to the motion of x1 into x1 minus sum of impedances common between m1 and m2 into x2 minus sum of impedances common between the m1 and m3 into x of 3 equal to the applied force. Similarly, for the second m2 and m3 we can write for m2 first we will write minus sum of impedances common between m1 and m2 into x1 plus sum of impedances connected with the m2 minus sum of impedances common between the x2 and x3 equal to the applied force. Similarly, for the m3 for third equation, this will be the general equation. You can write the equation. You can see. Okay, let me tell you. For sum of impedances connected to the motion of x1, what will be the forces connected with the m1? This is the inertia m1. You can write m1 as s square plus the frictional force, this frictional force Fv1, and this frictional force Fv3 into x plus the forces of due to these two springs K1 and K2, right, minus sum of forces, sum of impedances common between the x1 and x2, and what are these forces? Only K2, that will minus K2 x2s, and minus sum of impedances common between the x1 and x3, and what are the forces common between the x2 and x3? That will be the fv3 minus x3 of s equal to, and where we have applied force? We have applied force on the m2, so for first equation the applied force will be the 0. Okay, I have written these three equations. The first equation I have told you, and the second or third equation you can write in the similar manner. Okay, this is all about the translational mechanical system. Hope you will understand all the points which I have told you. You can ask me question if you have any query about this. In the next lecture we will start rotational mechanical system, and what are the basic components of the rotational mechanical system, and how can we find the transfer function of the rotational mechanical system. Okay, see you in the next lecture. Take care. Allah Hafiz.